recording. All right. So hello everyone. Welcome back to the PC seminar. And today we have with us Michał Włodarczyk from Eindhoven University of Technology. And he'll be speaking on Vertex Deletion Parameterized by Elimination Distance and Even Less. So thank you very much for joining us, Michał. And over to you now.
Hello, welcome everybody, and thank you for inviting me for the seminar. So this is a joint work with Bart Jansen and Jari de Kroon, also from Eindhoven University of Technology. And I will start my story with exemplary problem, well-known problem, odd cycle transversal, in which we are given an undirected graph, and the task is to find the smallest set of vertices such that removing them makes the graph bipartite. As you can see on the figure on the right, removing these two vertices makes it possible to partition vertices into yellow and blue sets, which induce independent sets. So odd cycle transversal has been studied for a long time through the lens of parameterized complexity with different parameterizations. And some most known examples are parameterization by the solution size, so by the size of the set S, or parameterization by some graph measures as tree width or elimination depth. And for each of these choices of parameterization, the problem is tractable. So an inspiring question is it a limit of tractability for this problem? Or are there some more easy instances, some more tractable instances with both large tree width or some other graph measure and the solution size? Or equivalently, can we find a parameter which is smaller than all of these and the problem would still be FPT? All right, so let me recall what are these basic graph measures. So first of them is elimination depth, also known as tree depth. It can be defined recursively as the smallest number of steps to make a graph empty. So for empty graph, the elimination depth is 0. Otherwise, we can remove one vertex from a graph and continue the recursive process on the rest of the graph. And if the graph is disconnected, then it's a maximum over all its connected components. Equivalently, we can define elimination depth as a minimal depth of an elimination forest of a graph, where elimination forest is a forest with vertices in one-to-one correspondence with the vertices of our graph, structured in such a way that adjacent vertices must be in an ancestor-descendant relation in this forest. And as you can see, if we are given an elimination forest of a graph of moderate depth, it allows us to solve some problems using dynamic programming and sometimes also in polynomial space. So the elimination depth treats empty graphs as trivial graphs. So we would like to refine this definition in such a way that bipartite graphs or some other target class of graphs would be considered trivial. So we can define something as an elimination distance to a class H. So you can think of H as an bipartite graphs as in our first example, or you can substitute here your favorite class of graphs. And as with elimination depth, the elimination distance to H can be defined recursively, with elimination distance being 0 for graphs belonging to a class H, and then through this recursive process where we remove one vertex from a connected graph and continue the process or when the graph got disconnected, we take maximum over all the components. And similarly as before, we can consider graph decompositions crafted to this measure. So we, similarly to elimination forest, we can consider H elimination forest, where instead of leaves in this forest, we can have arbitrarily large subgraphs which belongs to our class H, in this example, which are bipartite. And the depth of such an H elimination forest is maximal number of non-trivial nodes on every route to leaf path, where all these nodes which are yellow are considered trivial. So this is a first measure which we can define, which is considers subgraphs belonging to H as trivial. And now let us do the same with the notion of tree width. So a quick recap that a tree decomposition of a graph is a tree where each node is associated with a bag. It's a set of vertices of a graph, and the bags might intersect with each other. Each vertex of G should appear in a connected subtree of the tree decomposition, and each pair of adjacent vertices should meet at some bag. We define a width of tree decomposition as a maximal size of a bag -1, and the tree width of G is a minimal width of any tree decomposition. So how to make a definition of tree decomposition aware of our target class? The simplest idea is to allow arbitrarily large bags which belong to our target class H. So say they are bipartite. So we define tree H decomposition as a structure very similar to tree decomposition, but we allow bags which induce graphs belonging to the target class H and are adjacent to just one single bag. So the width of such a decomposition is defined as a maximal size of a small bag -1, and H tree width of G is a minimal width of any tree H decomposition. So before going into some more definitions, let us quickly see why this kind of decomposition still makes it easy to solve odd cycle transversal. So first of all, let us recall how the dynamic programming over tree decomposition looks for odd cycle transversal. And it's a dynamic programming routine over the tree decomposition. And for each bag, we consider its states, where each state is a partition of a bag in the vertices which are going to be deleted and vertices which are going to be on the left side of the final bipartite graph and the right side. For each state, we want to compute minimal number of deleted vertices in the subtree in the graph induced by vertices in the subtree rooted at this node. So everything that we need to do is to check if such partition is valid. So if there are no edges between vertices of the same color, and to collect information from children of this node. This is a very basic example of dynamic programming or over tree decomposition. So how to extend this approach to work with tree age decompositions? We just need to extend this dynamic programming to the case where our child node is a large bag. So how is the situation here? This bag might be large, but we know it belongs to our target class. So the vertices in here induce a graph belonging to our target class, here bipartite graph. So we need to solve a following subproblem. We are giving a state in the parent node, which specifies which vertices here are going to be deleted and which are on the left side in the final bipartite graph, which are on the right side. And we want to delete minimal number of vertices here within this bipartite subgraph in order to put the vertices marked orange on the left and blue on the right. And this turns out to be exactly the same problem that one comes across when solving odd cycle transversal via iterative compression. And such a subproblem is known to be polytime solvable. So this gives us a way to handle the large bags and make the problem solvable given tree age decomposition for age being class of bipartite graphs. All right, so let us make an overview of this class-aware parameters. So for any hereditary class of graphs H, we can define parameters H tree width being the minimal width of a tree age decomposition, and elimination distance to H being the minimal depth of an H elimination forest. So for both of these parameters, we can see that they H tree width is always upper bounded by tree width, because any tree age decomposition is any tree decomposition is also tree age decomposition, and also it is upper bounded by the deletion number to H, so the minimal number of vertices to remove from G to make it belong to H. Similarly, the elimination distance to H is upper bounded by elimination depth and the deletion number to H. But in general, H tree width can be small, and these two measures can be large, as we saw on the pictures. As we have the relation between tree width and elimination depth, that tree width is always upper bounded by elimination depth, the same holds for H tree width and elimination distance to H. The last important property is that if we consider class H of bounded tree width, then these new measures doesn't give us much, because then we can turn tree age decomposition into regular tree decomposition by extending the width by a constant. So these measures are only interesting for classes of unbounded tree width. So we are not interested in classes like trees or outer planar graphs, but rather bipartite graphs, planar graphs, chordal graphs, bounded degree graphs, and so on. So in general, we can define age deletion problem for any class of graphs, similarly as we did for bipartite graphs. So we seek a smallest set of vertices whose removal would make the graph belong to the target class H. So our goal is to solve age deletion problem parameterized by age tree width and by elimination distance to H. And in the latter case, ideally, we would like to achieve polynomial space computation, because algorithm parameterized by elimination depth can be sometimes made run in polynomial space. But we run into a very fundamental problem. So it is not difficult to define some complicated measure that would capture graph structure. But if we wanted to use it for solving vertex deletion problems, we should be also able to find the corresponding decomposition, so we can perform dynamic programming over it. In particular, we would need to solve an even simpler problem. So when given a parameter k, we would like to know if the H tree width of a graph is at most k, or elimination distance to H is at most k. These problems are FPT for measures as tree width and elimination depth, but for arbitrary target class H, it is a priori it is not even clear if such a parameterized problem would belong to class XP. So what is known about this problem? There have been some research in recent years about these graph measures, and what is known that when H is minor closed class, or equivalently, it is given by a finite set of excluded minors, then computing elimination distance to H is FPT. If H is given by a finite family of forbidden induced subgraphs, then it is also FPT, although it is not clear whether this algorithm can be made uniform. And also, if H is a class of graphs of bounded rank width, then computing H tree width is FPT. So there are two issues with this result. First of all, is that they are quite separated, that they apply to a particular family of classes, and it is not known if this generalizes. And the second issue is that these running times are really huge. And in the second item, it is not known if this dependency on the parameter is computable function. So the algorithm is non-uniform. So this seems as a pretty tough problem to compute these measures in general. So let us relax this problem, because computing it exactly might be overly demanding. So observe that we not necessarily need a tree-age decomposition of the optimal width, but we could work, we could make our dynamic programming work if we could find a tree-age decomposition of width comparable to the optimal. So we settle for approximation in finding these decompositions. So Here I'm ready to present our main contribution of our work, which says that for many classes of graphs, for example, classes given by forbidden minors, forbidden topological minors, forbidden induced subgraphs, or bipartite, chordal, or interval graphs, we can perform such an approximation. So in FPT time, we can find the tree decomposition of width at most polynomial with respect to the optimal width. So this function h can be made polynomial. And the same holds for the elimination distance to these classes. Since we started with example of bipartite graphs, let me focus on this particular application and show how this theorem looks for the case of bipartite graphs. So there are three algorithms, and first is approximation algorithm that computes an H elimination forest with this approximation ratio, and this algorithm works even in polynomial time. We can improve this approximation ratio a bit, but when settling for a worse running time and exponential space. And for H3 width, we also can compute 3H the composition of width k cube, where k is bound on H3 width in moderately exponential time. So both these approximation factors and these running times are relatively moderate. So I try to argue that this leads to an efficient computation. So now let me shortly describe how to find these graph decompositions, focusing on a 3H decomposition. And this will be a high-level outline. So suppose that the graph has bounded H3 width, so it admits some unknown 3H decomposition of width k. So suppose we are given a vertex from a large bag, and we are promised that this vertex V belongs to a large bag, and some problem that we want to solve is to find a good candidate for this bag. So we want to find some vertex set C that includes V, which would have a small separator of size at most k+1, that would separate it from anything else in our graph. So let us formalize this as an HK separation. This is a pair of vertex sets CS, such that C induces a graph belonging to a target class. The neighborhood of C belongs to S, and S has bounded size. And we would like to be able to find such structures to cover a given vertex V. And we define a subproblem called H separation finding, where the small h is some function. Here we are given a graph, a vertex, and an integer k, and we either want to find a separation CS so that V belongs to C and the size of S is at most h of k, or conclude that there is no such hk separation. So this function small h is the approximation factor in this subproblem. So now I will quickly say what's the link between separation finding and constructing the compositions. So the outline for decomposing a graph of finding 3H the composition is as follows. First, we execute this separation finding subroutine to partition the vertices of our graph into sets that would cover the large bags. So each large bag in the unknown 3H decomposition would be contained in some set in this partition. So now we contract all these sets, we obtain some quotient graph, and we prove that because of this property, the tree-width of G prime is upper bounded by H tree-width of G. And now we can use known algorithms for computing tree decompositions to compute the tree decomposition of G prime, and then using properties of HK separation, we can go back to G and turn it into 3H decomposition of width depending on the K and H. So, and similar procedure also can be done for computing H elimination forest. The main message of the slide is that when we can solve H separation finding approximately, then we can find 3H decomposition of approximate width. So let me now focus on this subproblem on separation finding, and again I will show how this works for bipartite graphs. So we are given graph G with a specified vertex V, and we want to find possibly arbitrarily large vertex set C that induces a bipartite graph but has small neighborhood. So we create an auxiliary graph G prime in which each vertex V turns into two copies, an odd parity copy V prime and even parity copy V double prime. And for each edge UV, we create two edges that connect vertices of a different parity. First, observe that if G was a bipartite graph, then in G prime we could never find the walk from V prime to V double prime, because every step in such a walk would change our parity. So we would alternate through the upper rectangle and lower rectangle, and after any walk of even length, we would arrive at the same parity. This is not true if the graph is not bipartite. And an important observation is that when we have a HK separation covering V, so that V is contained in the C, in the set C, then when we look at the set S and take a union of all its odd parity and even parity copies in the graph G prime, then they would form a V prime, V double prime separator in G prime of size at most twice the size of S. It should be V prime, V double prime here. So we can construct the graph G prime and just look for a minimal cut between V prime and V double prime, and we are, if such a HK separation exists, then we are guaranteed to find a cut of size at most 2K. And this cut might look arbitrarily, but we can always turn it into a set S of the same size that would separate G from everything non-bipartite, so from every odd cycle. So by this simple observation, we can solve H separation finding for a function h of k being 2k. So this, as already mentioned, this already gives us all the machinery to construct 3H decompositions of approximate width. As another example, let me talk about separation finding for graphs excluding and induced subgraphs, and in particular, let us focus on claw-free graphs. So claw is an induced subgraph of this shape. So one vertex connected to 3 vertices which are not connected to each other, and graph is claw-free if it doesn't admit such a structure as an induced subgraph. So if the graph is claw-free, then we don't have to do anything. Otherwise, we can find some claw in polynomial time. So how a HK separation can look like in such a graph? So there are 2 options. Either this claw is behind the set S, so it belongs to a different connected component of G minus S than V, or it intersects this claw. It cannot be a situation that this claw is contained fully in the set C, because we wanted C to induce claw-free graphs, claw-free graph. So we have these 2 cases. In this case, if the intersection of S and the claw is non-empty, then we can guess which vertex of this claw belongs to S, and we can reduce our problem. We can remove this vertex U, and since we guessed it to belong to S, we can decrease our parameter by 1, and we can recursively solve this problem on G minus U with a smaller parameter. So that's easy. The second case is that when the claw has an empty intersection with S, but then it means that for any vertex of the claw, S is a UV separator. So let me recall the definition of an important separator. So a separator, UV separator, is important if there is no other separator of no greater size that is further than our separator S prime. What does it mean further? It means that a set of vertices reachable from U would be a superset of the vertices reachable when using the first separator. So here on this picture, we can see that the separator S is not important because the separator S prime is further than S. But now we can see that if there exists such a separator S prime, that this structure is also HK separator covering our vertex V. So if we are able to push some subset of S towards V, then this part of the graph would be still claw-free. So there is we can formalize this observation with a lemma that if S was a UV separator, then there exists some important UV separator, S prime, and an H case separator, so that S prime is contained in the set S. It is well known that for two given vertices UV, the number of important separators of size at most k is bounded by 4 to the k. And these important separators can be enumerated in within this running time. So what we can do, we can enumerate all these UV separators, and for each of them, we can again branch. If we guessed this correct important separator, then we can forget all this part of the graph that is separated from V by S prime and focus on this subgraph, and again decrease our parameter by the size of S prime. So in both of these two cases, whether S intersects the claw or not, we can find some branching rule and simplify the problem and continue this recursive process until we reach a subgraph that is claw-free. So by extending this idea and using some other properties of different graph classes, we can also use this observation to solve separation finding for planar graphs or chordal graphs or other graph classes in question. So let us summarize what I have already said, that when we can solve the separation finding problem with an polynomial approximation ratio, then we can use it to construct a 3H, the composition of with polynomial with respect to the optimal one, and the same works for constructing a elimination forest. So now we would also like another meta theorem, which would allow us to say that really solving H deletion is FPT parameterized by H3 width. So now I like to talk on what the properties of H are necessary to make this work. So the first property is related to the idea of gluing graphs. So a k-boundaried graph is a graph with k specified vertices, which are labeled from 1 to k. And when we are given two k-boundaried graphs, we can perform a gluing operation. So we identify these vertices with respect to their labels and construct a new graph. And we require that the edge between two vertices from the boundary should be either present on both sides or on neither of them. Otherwise, the gluing operation is undefined. And we can define a following equivalency relation over boundaried graphs. So we say that boundaried graphs G1 and G2 are equivalent when, after gluing any other graph H, this gluing product belongs to target class H, if and only if this gluing product belongs to the class H. For example, for bipartite graphs, the two boundaried graphs would be equivalent if the odd and even cycles enforce the same relations on the boundary. And we say that H membership is finite state if for every k, for every size of boundary k, this relation has finitely many equivalency classes. So actually, when we think what standard vertex deletion algorithms over tree decomposition do, they implicitly rely on this fact that this relation has finitely many equivalency classes, because when this would be a bag in our tree decomposition, we can imagine what happens in the bottom part in the subtree rooted at this bag and on the other side of the graph, and we only need to remember in which equivalency class we want to end up, and this is why we only need a finitely many number of states per bag. So if the H membership is finite state, we can define a following function R of k, which is the maximum size of the smallest k-boundaried graph in any equivalency class of this relation. In other words, any k-boundaried graph should be equivalent with respect to this relation to some graph on at most R of k vertices. And it turns out that for many graph classes, this function R doesn't grow too rapidly, and often it grows polynomially and even linearly. Okay, and the last ingredient that we need is related to the following auxiliary problem, which is H deletion with undeletable vertices. So this is a generalization of our H deletion problem, but additionally, we are given a vertex set X, and we want to find a solution which is disjoint from X, or report that such a solution doesn't exist, and we consider this problem parameterized by the solution size. And for many classes, the known algorithm solving H deletion parameterized by the solution size can be adapted also to work in this more general setting. All right, so with this, I'm ready to formulate the second meta theorem, which says that whenever hereditary class H is closed under taking disjoint union of graphs, H membership is finite state, and this problem, H deletion with undeletable vertices, is FPT, parameterized by a solution size, then we can solve H deletion in such a running time when given a 3H decomposition of with T. And for example, classes that satisfy this preconditions are bipartite graphs, chordal graphs, graphs given by a finite family of forbidden induced connected subgraphs, or by finite family of forbidden connected minors. So observe that in the previous meta theorem, we didn't have to assume that these minor abstractions or subgraph abstractions are connected, but here it is not necessary, because otherwise the class might not be closed under disjoint union of graphs, and the H membership might be not finite state. All right, so we can fill our picture with following arrows, that once we are able to construct 3H decomposition of moderate width, we can check if our favorite graph class satisfies these two conditions, so the problem is solvable when given 3H decomposition, which makes our H deletion problem FPT parameterized by H3F. And some other theorems from this work that I didn't have time to cover related to solving H deletion parameterized by elimination distance to H, which is this parameter is always lower bounded by H3F. So this is only interesting when we can solve a problem in polynomial space. And for some classes, we also show how to do this. And also, apart from solving H deletion problem parameterized by H3F, we can also consider different problems. For example, it is known that vertex cover is polytime solvable for bipartite graphs and for chordal graphs. So we can use this fact to solve vertex cover parameterized by H3F for any of these classes. So this was all that I wanted to share with you. I hope that I covered your favorite graph class, and if not, then the paper should be soon on arXiv, and you could check if your favorite graph class is covered, or otherwise I would be happy to answer any questions. Thank you.
Thank you for the great talk, Michał. And I guess we can take a few minutes for questions. So if anybody has questions, you can just unmute yourselves and ask, or you can type in the chat if you prefer that.
Thank you for the talk. So I have the following question. So suppose we have a graph class, say H, defined by monadic second order logic property.
Mm-hmm.
Do you know
Yep.
any example of such a class such that deletion is FPT, but elimination distance becomes hard?
You mean that solving the problem parameterized by a solution size is FPT?
Yeah.
But computing elimination distance is W1 hard?
Say W1 hard. I don't. It doesn't matter.
So we don't know any such example. For the case of perfect graphs, we know that both are W1 hard. But we don't know any class with such dichotomy.
Okay, thank you.
Any more questions? Seems not. In that case, I guess we can conclude. So I'd like to thank you once again for accepting the offer and for giving this wonderful talk. It was great to have you. And yeah, thanks to the audience for being around. We conclude our session here for today and see you all next week. Thank you. Bye.
Thank you. Bye-bye.